Yeah, we are now aware that BJT is going to operate in three types of configuration, right? We have three types of configuration: common base, common emitter, common collector. Okay. In previous lecture, we have seen the operation of the common base configuration. Now we will try to understand the common emitter configuration. So this is the circuit for the common emitter configuration, right? As we are aware now, the what is the output and what is the input, right? So IC collector current, right? That is going to be what output, and IB is going to be what input, right? So yeah, we have the two circuits, output circuit here, right? From this collector terminal, then this RE, then VCC, and then again back to this voltage VC that is going to appear across the collector to an emitter, right? So this is what the output circuit, and input circuit is what from this base terminal, right? Base terminal, then this voltage will to be VB, right? Base to emitter voltage that we are going to apply, that going to appear, or we are going to provide, so that this junction base to emitter is going to be forward bias, right? So this is input, yeah, input circuit, right, up to this RB, right? And yeah, of course, VB is the potential that we have to maintain across this base and emitter, and while the VC is the potential that we have to maintain across this collector and emitter, so that those charges must be attracted toward this collector from emitter, and so in the opposite direction, IC, the current is going to flow, right? The IC, that is collector current, towards this emitter, right? That in emitter there is going to be emitter current, right? And input, the base current, right? So output is collector current IC, input is base current IV, right? So output circuit and input circuit, both the output circuit and input circuit, they have a common terminal of this transistor, that is what emitter terminal, right? So that's why this configuration is called common emitter configurations. Okay, what do we have the advantage over this common base yeah, transistor, that we have to learn, right? So as we are aware that this IB current is going to be what the input to the device, and IC is going to be the output current. So the minor variation in the IB, that is going to reflect in this fluctuation of the IC also, because we are aware of this formula: I is equal to IC plus IP, right? So that we have to verify. So how? By applying this potential, right? The VBB that is going to be connected at this base terminal, and VCC that is going to be connected at this collector terminal, right? And we are going to plot by varying those current flowing through this base terminal, right? And we are going to observe how this collector current is going to vary, and with respect to the VCC and with respect to IB, right? We have to keep first this IB, right, whatever off, and we have to apply certain voltage right across the VCC, so that this collector base is going to go to reverse bias or off condition. Then whatever the minimum current IC that we have to observe, and then after that, what we are going to do, we are going to vary this IB current, that is base current, right? Okay. And as soon as this base current will increase, so we have to observe the IC for particular value of the base current, and then we have to vary this VCC, and for a particular value of IB, while varying this VCC, we have to observe what is going to be the effect on this IC. So this characteristics is called what, the input characteristic that we have to draw on. And it means input and output characteristic, two characteristics we have to learn, that is when we apply current at this base terminal, so what kind of current is going to flow through this input circuit, and at the same time what is going to be effect on this output circuit when we vary this IB current, that we have to learn. So suppose, yeah, input characteristics, so input is what base current, and we have to maintain the base emitter voltage and across this junction, right, emitter junction. So input is going to be drawn between what the base emitter voltage and the IB current, base current, that is going to flow through base, right? So we have seen the similar characteristics of PN junction diode, right? Is of course it is a PN junction diode, P and N junction diode, right? So VP is voltage across this PN junction, and IP is going to the current flowing through the PN junction. So as that PN junction was having the characteristics, the similar characteristic we are going to get for input characteristics for this BJT, right? So we are going to plot this uh, IB current, base current along what the potential across the base and emitter, that is VB. So as soon as VB is increased, so as we are aware that this junction is nothing but a PN junction, yeah, this is a PN junction. So in order to turn on in forward bias this PN junction, that we need to apply what minimal threshold voltage, right? And that threshold voltage what nearly what 0.7 that we already learn in the PN junction diagram. So as soon as we apply the 0.7 volt or more than that voltage to this yeah, base emitter junction or base emitter terminals, then this device is going to be, yeah, it means, or this junction is going to be forward bias, and we can say that this device is going to turn on, right? Yeah. So after this 0.7 voltage base to emitter voltage, this junction will, this depletion layer will vanish and current will try to flow. That is the base current from this base to emitter, right? Yeah, this is the way that current is going to flow. That we have to remember. And it looks like the forward characteristics of the PN junction diode similar. Okay. So as soon as the voltage VV is going to vary, increase, so the IV current is going to increase linearly. But after which, after up this threshold voltage only, and before that, only very minute current. This we red line see, it is not zero exactly. It is something very very minute in the microampere, 0.01 microampere, nanoampere, right? That means. That very minute current means so that no operation is happening within this device. We can consider no device is not in working condition, yeah, because it don't have that current so that this circuit can be okay, driven, right? Okay. So before this threshold voltage, this device is off, but after we applied this threshold voltage of 0.7 volt, this device is going to turn on and the current is going to start flow linear fashion, right? That we have to. Right, and then what is going to be the input resistance for this device? Input resistance, of course, we are applying this in the input to this base, so input resistance is going to be offered by the device, and that we have to calculate with the help of this slope of this curve, right? So input resistance of this device is called is calculated about where a change in base emitter voltage to the change in base current, right? That is the formula, right? And at that time we have to keep VC constant, right? Whatever the VC that we are going to apply between this collector and emitter, that we have to keep constant. And when we vary this base to emitter voltage, so we will get the variation in the this input base current, right? And so this ratio of change of base emitter voltage to the change of change of input base current, that will give you the input resistance of this device. Okay. So this was the input characteristics, and let us see the output characteristics that we have to draw between what the output voltage, that is VCE, right? Collector to emitter voltage, right? And output current is IC, right? So we are going to plot this yeah, collector current IC across this collector to emitter voltage. And yeah, so what we have done, we previously we kept IB0, right? As we discussed earlier, right? We have to keep this IB first 0, and when we keep this IC 0, and we have to vary this whatever the voltage VC, right? So as soon as we vary the increase the voltage VC, what we find when IB equals to 0, we get a certain straight line, not a very huge variation, right? And we can say that when IB is equal to 0, yeah, now we get a because this junction is off, right? No current is going to flow from emitter to collector, right? So the high, very high potential, not potential, but very high resistance will be offered within this collector and emitter, right? Very high resistance between collector and emitter. So we can say that no current is going to flow. So the value of IC we will get in very small milliampere, so that this output circuit will not get triggered, right? And that is going to happen, right? And so we can say that below this current, this transistor is an off state. Below this current, this transistor is an off state, and we call this state as the cutoff region, right? That we already discussed those different cutoff region, saturation region, active region. So that operation we have to see, right? So this is the cutoff region when what IB is equals to zero. IB is equals to zero means what? This junction is off, right? This junction is off means what? Base to emitter junction is off. So of course there is going to be high resistance present, and where the collector and emitter, of course they are in reverse bias, right? This collector which is n type, right? Right, it is connected to positive, so means this is the reverse bias condition at this collector junction. So this is also going to have a very high input, high resistance, right? And so this device is off, right? So we already discussed all these things. So because of that, this device is complete off, right? Both junction B and C collector, right? These are offering very high in resistance, right? From input and this output also. So because of that, no current is going to flow from this IC to I, right? And so we will get a very constant minute plot, very minute current because of the minority currents, right? Minority charges, and it is going to be very small, at the order of microampere and ampere. And we can say that this device is turned off because that very small current is not going to drive this whatever the load resistance that we are going to connect to this at output, right? So you can say that this region is cutoff region where the device is off. So it is happening when IB equals to zero, right? And now what we are going to do, we will increase this current IB to something value, right? 2 ampere suppose here. And when we keep this IB equals to 2 ampere constant, right? We have to keep this IB equals to 2 ampere constant, right? And we have to vary this VCC or VCE. Okay, so this is the horizontal axis. We see where we are increasing 1, 2, 3 volt, right? So IB is constant, but as soon as this VC is increased, we see that this current is going to be somewhat increased, right? Somewhat increased, right? And further, if we increase this IB current again to more values, right? And we can suppose IB is equal to 4 microampere, and we keep this constant. And again, we have to vary this collector emitter voltage. We see. So for this increase in IB current, right? What we get that IC is also increased. And suppose again we make this um, experiment again, means increasing this IB, so we will get again this curve, right? This curve, right? This horizontal curve is going to be shifted upward, right? This slant lines, these are going to be more shifted, right? Means there is going to be increase in current of collector current, right? So this is how collector current is affected by this input base current, right? Input base current. So right, so this increasing the slant plot, right, or line, it is the current IC is increasing according to what the yeah base current that we have applied. So this is a region where we can say the current is going to flow, right? The current is going to flow. But we can observe that this voltage range of the collector to emitter. So as soon as we increase this smaller voltage, there is a real relationship between this current, and it is increasing in smaller way. But it is again related to IB, that as soon as this IB increase, this curve is going to shift upward side, right? Means IC is going to increase. But this is the slow variation with respect to the VC, right? This is the slow variation with respect to VC, but it varies very fast with what IB, right? That we can observe here. But okay, so this region of operation, or this region of operation, right? This is called what? The active region. So above this cutoff region, means above this IB equals to zero, this region is what? Active region, where this transistor is going to be, used as amplifier. We can observe that for smaller value IB, we get a larger value of ICs, right? So we are going to use or operate this transistor in this active region. Okay. Now what we are going to do is that, yeah, so what we are going to do, uh, we are going to make the base emitter, base emitter forward bias, right? And at the same time we are going to make this collector and emitter also forward bias. So what will happen, when this collector and emitter is going to forward bias? So we observe that this junction, collector junction, is going to be turned on, right? It is going to be forward bias. So even the smaller current we are applying here for ip, we will get the maximum variation. So we can observe, as compared to this active region, even the smaller voltage of vc is increased, we can get the maximum current, right? A larger current as compared to the active region. Then we can see this, these are somewhat slant in active region, but it is, it is in saturation region we get more maximum current right here as compared to this, right? Now for 1 volt, you can see it was a very minimum current for ib, but for 1 volt it is getting maximum current, right? For 2 3 volt you can see there is a minimum current, but this current can get at only 1 volt when compared with this active region, right? If device operating in 3 volt in active region, we whatever the amount of current right was here getting, the same amount of current we can get in saturation when we apply only half voltage of only 1.5 voltage of we see, right? So what is happening, maximum current is trying to flow throughout this resistor. So even small variation in vc will give you a large current, right, as compared to these other regions, active regions. So we say that this base emitter and the collector base is both are forward bias, and so maximum current is flowing whatever the supply we are attached here. So for that, whatever the supply that is going to appear across this region, and maximum voltage or maximum current we are going to get. So this region is called saturation region, the maximum output we are going to get. So that is how three regions we are going to categorize according to the whatever the voltage or the biasing condition we have applied along this uh, transistor device, right? So we have three regions: cutoff region where we can get we get this when ib is less than zero, right? So this lower region is cutoff region, and what is active region? Above ib is equal to zero and before this line, right? This is the active region where we are going to use transistor as amplifier, and now and before this plot, right? This line, that there is a region called saturation where we get maximum output even though smaller variation in ib or input is made, right? Okay, so these are the three regions that we have to remember. So this is what output characteristics, right? Yeah. And when it comes to the calculation of gain, right? So yeah, gain we have to calculate, of course, because it is an amplifier, that there is going to be some amplification of current. So of course we see that for smaller value of ib current we get a large variation in this ic. So there is going to be increase in collector current, that is output current is collector current with when it compared to the base current. So by how much amount, the collector current had increased. So simply how we are going to calculate this this output current upon input current. So output current is ic and input current is IB. So the ratio of ic and ib means ic upon ib will give the value that by which this collector current has increased, right, as compared to the ib, right? Yeah. So with similarly voltage, okay, so when it comes to voltage, whatever the voltage we are getting as output with respect to input, we can say that voltage is increased, but by what, by which amount, by how much amount, right? So it is going to be what, output voltage upon input voltage, that ratio will give the by amount by which output is going to be increased, right? Output upon input voltage, similarly output current upon input current. This is the gain, means extra that again that that output circuit is going to deliver, right? Means yeah, ib into some value is going to be what, ic. So how much? So ic upon ib, that much gain. So we call this amplification factor as beta. We call this amplification factor as beta in case of common emitter amplifier, and it is found to be equals to 20 to 250 times. Means what? If we apply this 4 microampere current here at IB, so if the gain of this device is 20, right? So 4 into 20, so 4 microampere into 20 means 80 microampere current will be available, will be generated at this collector current IC. So that we have to remember. So, but in case of common base, yeah, in the case of the common base configuration, the amplification factor was alpha DC, right? Of course, alpha DC is what the amount of charges that is going to, um, uh, yeah, amount of the charges that going to be delivered from emitter to collector. So there was 0.95 to 0.99% of the charge. So that was the gain. But we know that this device, the same device was in common base configuration, common emitter configuration. So the same physics is going to happen in both, but only gain is going to vary. So how the gain is going to vary, that we have to calculate in terms of what the this amplification factor of alpha. So beta is alpha is going to be dependent on amplification factor alpha, because alpha is going to determine the percentage amount of the charge that is going to flow from emitter to collector, right? So of course alpha is going to define the beta factor, that is amplification factor in case of common emitter convection, right? So how it is related? So suppose alpha is equals to what? IC upon I, because in right IC upon I that we studied in previous lecture. So beta is equals to what? Beta is equals to what? The collector current upon IB, right? So, right, input output current upon input current. IC is in output current and IB is input current. So that is going to what? Amplification factor beta in case of common emitter configuration, IC upon IB. So yeah, we have the relationship, right? Is that IE is equal to IC plus IB. IE is equal to IC plus. So we will put those values within this equation, right? And as IC equals to what? Yeah, IC equals to alpha IE, right? Right, IC, right? From this equation, right? This alpha is equal to IC upon IB. This will give IC equals to alpha into IE, right? Alpha into IE, and right. And so when we put those values within this relation, we will get a relation that is alpha equals to beta upon 1 plus beta, or beta equals to alpha upon 1 minus alpha. So this is how we have to, these are the gain which are the related to each other, alpha and beta, that we have to remember. So beta is equal to alpha upon 1 minus alpha for common emitter amplifier, right? And alpha is the gain for what? Common base amplifier, that we have to remember, right? Yeah. So that was a common emitter. Now let us see the common collector. So what we have to do in case of the common emitter, right? We have this emitter in common between this output terminal and input circuit. Now what in case of the common collector? So simply these terminals are interchanged, right? Right. This emitter will go toward this upper, and this collector will toward go into this lower side, right? So this is toward the circuit, right? So this emitter, right? So this is going to be what? Output circuit, and this is going to be what? Input circuit. So IB is input current, and I is going to be the output current. Remember it, right? So this is how the configuration should. So but what is the possible effect, right? So when it is compared with this common emitter configuration, we see that this collector is what? P type material. This emitter is also P type material, right? So even though we interchange, so what we are going to get, this upper terminal is a P type region, and our lower terminal is P type region as well. So there is not going to be much more variation when it compares to the common collector with this common emitter. They are going to follow the same rules, right? Same equations, all those, right? But because of the forward bias and reverse bias condition, there are of this junction, right? Base emitter and the collector base, right? We will have certain different characteristics. So when we compare all those configuration with each other, right? So this is the table where we have done the comparison with this all those common base, common emitter, and common collector configuration, right? So what is happening, that we have to remember here, right? Yeah. So for common base, the input is for this base, right? And yeah, of course, it is from base. The base is common between input and output common emitter is common between the input and output collector is common between input and output, common collector configuration, right? And input current, right? Input current in case of common base is IE, right? Common emitter IP is going to be input, and in case of common collector IB is going to be the input current. But in case of the output current is going to be IC in case of common base, and IC is case of common emitter, and IE in case of common collector, right? And current again in case of the common base configuration is alpha DC, right? And then for common emitter, it is going to be the beta DC. This will be IC upon IB. While in case of common collector, it is going to be what? Gamma equals to IE upon IB, right? And yeah, what are the different values? So in case of common base configuration, it is having the laser value. The gain is laser in case of common base configuration, while in case of common emitter configuration, the value of those yeah gain beta again, right, that is going to be high, right? And in case of common collector, it is going to be very high. Okay, that we have not to remember, right? Okay, so input voltage VEB for common base, VB for common emitter, and VBC for common collector. That output voltage is VCB for common base, VCE for common emitter, and VEC for common collector. So it's some variation. Yeah, that we have to remember. The input resistance that we have studied. So in case of common base, it is very low, and the output resistance, it is up to order of 1 mega ohm. So what is happening? So it is offering very less resistance. So it is used for those those signals only with some smaller signal frequency as a pre-amplifier, right? To just boost a particular signal, right? And to yeah, and then common emitter, right? So we see that high gain, right, at the rate of 1 kilo ohm input resistance, and the output resistance is going to be what, high up to 40 kilo ohm. So this particular they have a actual gain that we require to amplify a particular signal, right? And that's why it is going to use for an audio amplifier. And that is whatever the frequency that we are having from 20 kilohertz to 1 megahertz, 2 megahertz, 100 megahertz, right? All those, right? And common collector configuration, what is happening, right? What is happening? The input resistance is very high, 500 kilo ohms. So very less input current is going to flow, and as compared to this output, right? And output resistance is very low, 50 ohm, very small, which is not the required condition for the amplification, right? What we need, less input resistance and higher output resistance. So this is the reverse condition of what is happening with common collector. So we cannot use this as an amplifier circuit, right? So as it is going to offer a very high or input sorry have a very high output resistance, so what it is used for, it is used for a method called impedance matching, where we have to match, or we have to deliver a proper power, whatever the power from one terminal to another device, from one equipment to the other equipment, from one circuit to other circuit. You have to deliver the power from one circuit to other circuit without loss. So for that purpose, what we have to do is we have to match the impedance of the both the circuits, right? So that impedance circuit has to place between the both circuit, so that the impedance is matched. So whatever the power from one circuit to another circuit, that can be delivered. Good. So that is the very important, right? So voltage gain that we are seeing that it is for count base nearly equals to 1, right? Nearly equals to 1, 0.99 or 0.95, nearly equals to 1. But in case of common emitter, it is more than 1, that is equal to 20 or 20 to 50, or we can adjust it, right, by whatever the components they are going to be there. And then in case of common collector, of course it is reverse, so it is having the 1 less than 1 gain, right? So this is what the different company, kind of the thing that we have to remember, right? A very important thing, very important thing that we have to remember, that the phase, right? So during the operation, right, during the operation of the circuit, right, what is happening exactly, right? So for a signal, we have the three parameters, right? Amplitude, frequency, and the phase. So what is happening? The amplitude is increasing, right? Amplifier is going to amplitude. But what about the frequency? The frequency is going to be remain the same, whatever the changes at the input of this Yeah, transistor is going to happen. The similar frequent changes is going to observed in this. So frequency is going to change, but this phase is going to shift by 180 degree for common emitter. But in case of common base and common credit, it's going to be 0 degree, right? That is only very difference, right? That okay. So that was the comparison between these different types of configurations of these transistors.